Hello. In this section of the lecture, we're going to set the stage for the moment that we're in now and talk about a history of language models. I'm going to start by going over a quick definition of what language models are, and then go over the last few decades of language model applications, namely, like, what are they useful for? And then I'll sort of do the first half of a recap of language modeling research, and then Jad, Suyash, and Hung and Shane will do the sort of more modern stuff. Okay, so as a motivating example for language models, which we'll be coming back to a few times in the next 10 minutes or so, let's consider autocomplete. You probably use autocomplete all the time, maybe as you're typing in searches into Google or writing text into a word processing document or composing an email. And if you've done that, or if you've used those suggestions, then you're using a language model. So let's just take this case where I'm writing a message to my friend Martin in California. Dear Martin, how's California? Boston weather is blank. So an auto suggest interface might at this point suggest words like hot, cold, frigid. That knowledge is essentially what a language model excels at. And so what is a language model? So for our purposes, it's a probability distribution over all sequences of words that might be spoken or written. In particular in some language and in some context. Imagine that the Gmail application that I just showed you. I'm running it on my phone or on my laptop, but it's talking to a Gmail server, which has something like a language model that has some representation of all of the possible things that I might write, like every sentence in the language. You can imagine in this table here, you see them alphabetized from aardvarks ate apples all the way down to Zizix, Zork, Zaphod. For each possible sentence that might be spoken, there's some probability. The language model is a representation of what the probability for each of those sentences is. Now, there could be a very, very large number of sentences. I mean, there's probably, an infinite number of things that I could reasonably say. So the language model has to sort of responsible for apportioning out all of this probability mass, all of the different possibilities. So here I've excerpted the ones that, or I'm highlighting the ones that start with Boston weather is, which is also what I typed in the email to Martin. And so you can imagine the language model, knowing that I've already typed that, can now sort of focus its predictions on the things that start with Boston weather is. So imagine that it takes kind of this table and it looks for, to decide what to show me as a suggestion, it takes all of the words that follow Boston weather is, and then it sorts them by its modeled probability of the word given the left context Boston weather is. If it's a certain kind of model, like a generative model, it's particularly easy to kind of access these completions in an efficient way. Oh, this is a sort of New Yorker cartoon that just came out a couple days ago that I thought was pretty appropriate for this part of the lecture, because it's sort of referencing the kind of AI debate that's ongoing. It says to think this all began with letting autocomplete finish our sentences. So yes, so autocomplete is in some sense the quintessential application of language models that we'll be coming back to frequently in the class. So now let's talk about applications of language models. So the first 30 or so years, 20 to 30 years of language models, they were typically used as helpers, meaning the probability distribution was paired with some other task. The actual system could be seen as decomposed into a language model and then sort of something else that it was helping out. The simple example is the autocomplete interface for a search engine, in which you're typing something to kind of condition the model to sort of focus it in on the things that you might want to see, and then it does the language model then does the work of if I've started to type Boston W, language model, and it produces completions that start with Boston and then the letter W. Another very classical application of language models in this kind of helper paradigm is speech recognition. And I say classical because speech recognizers really in the last 5 to 10 years aren't new speech recognizers anyways, are not architected this way. But kind of old school speech recognizers, you'd start with an audio waveform, extract some so-called features of the waveform, and turn it into maybe someone who's worked in signal processing will recognize this as a spectrogram. Kind of extract the sort of frequency-based features from the signal. That gets kind of input into what's called an acoustic model, which is basically which will tell us, like, for every word in a vocabulary or for every sentence, what's the probability that we see this signal given that it was that word. That's then paired with a language model, which is kind of just telling us what words are probable. Those two things combined kind of give us a decoder, or sort of feed into a decoder, which will then tell us would give us a ranking of all of the strings that were spoken that incorporate both the acoustic and the linguistic knowledge. Language translators classically were also written to use language models as helpers. You might imagine here's a kind of a simple architecture for something that translates, a system that translates between English and French. It might first translate each word one at a time, and then use a language model, because clearly if I do that for English and French, it's going to get word order wrong, among many other things. But we might use a language model to sort of reorder. After doing the word by word conversion, we might use the language model to find out what the best order is for the words in the target language, and then maybe do some other things to sort of fix it up in the target language. More modern applications of language models, like in the last 5 years or so, have been more generative rather than as helpers. So by generative, we mean that, generative is a little bit overloaded in this field, but in the sense in which we mean generative AI or generative language models, is that we can use the language models to produce text directly. If you build a language model that is really good at predicting the next word, you can use it for all sorts of interesting generative tasks. So this is the examples page from OpenAI's GPT-3 API. You can see sort of starts with Q&A, like you can actually ask prompt the language model with the question and then get back an answer. Possibly right, possibly wrong, but and we'll get to how to measure that later in the class. You can also use it for correcting the grammar or changing the style of, or otherwise like improving some text that you've already written. You could use it for summarizing things for different reading levels, generating commands. So many different things become possible when the model is kind of accurate enough to be used in a generative way. So next I'm just going to talk about what the life of a language model is. So if you squint your eyes, and every language model can be seen as coming to life in approximately this way. We got a pile of books on the left just to represent a bunch of so-called training data. And it's important to note, I probably should have put some sort of people on on the left side here. Each of these books, or each of the sources of data that go into a language model were created by some person or people. But the important thing here is that we have some human created text, which kind of represents the kind of information that we want to be able to predict with a language model. So the larger language models that we see today are trained on a good chunk of the publicly available internet, such as like all Wikipedia articles and probably other sources too. But just and sort of public domain books and lots of other sources, some of which are undisclosed in the more recent models. But in any case, you start with some large amount of training data, and then typically to build a model, you might curate that set, or you might select from that set in some way, and then select text from those sources in some way, clean the data in a certain way to throw out portions of the set that you don't, that are either problematic or messy, or that you don't care about for one reason or another. You then train a model to kind of directly predict the next word or next words, as I just showed in the earlier slide. And then we'll talk about this later, but more modern models have a sort of fine-tuning stage where maybe we tweak it to align the predictions with human preferences in some way, or tweak it to be suitable for some particular kind of application. And then we take that final language model and integrate it into an application, such as a search engine. I've put arrows to these little evaluation boxes here because we'll be discussing evaluation a lot in this course. At all points, we want to evaluate the quality of this process, not just of the raw language model, but also the sort of suitability to the task of this evaluation. And then once it's integrated into an application, we want to measure the efficacy of the application in some way. And then once the application is deployed in the field, ideally we would then evaluate the impact of the application on the users and perhaps on non-users as well. Okay, so now let's just talk about language model research going back to the dark ages, by which I mean, I guess, 1980s or so. The very simplest language model I think you could possibly imagine is what's called a unigram model or a 1-gram model. And a 1-gram model, as I recall from the second slide, that language model, it's just assigning probabilities to every sentence or every string in the language. The 1-gram model just decomposes the probability of a sentence into the independent word probabilities that it then estimates from data. So the probability of someone speaking the sentence "Boston weather is cold" might be probability of Boston times the probability of weather times the probability of is, and then probability of cold followed by an end of sentence marker. There are many problems with this kind of a model. It's very simplistic. So for one thing, it ignores word order. You can see I could swap these probabilities and it wouldn't make any difference. It ignores context. But on the upside, they're really fast to train, because all I have to do is to estimate probabilities of someone saying the word Boston is to count the number of times that Boston appears in my training corpus and divide by the total number of words. There you get a good approximation to the probability. But these models, unigrams, and really n up to a small n, are really not good. And I'll show you an example of why in a few slides. But let's just talk about the kind of generalization of, or the sort of next step would be, instead of modeling with single words, modeling with windows of n words. So n-gram models, which you could consider to be sort of like the OG generative language models, are trained by sliding one of these windows. This is like n equals 2, sliding a 2-word window or an n-word window over the training data and counting the number of times each combination of n words appears. So it's kind of a generalization of the unigram thing that we saw. It's this is based on what's called the Markov assumption. This is the kind of 2-gram version of the Markov assumption, which is saying that the probability of the next word, given all of the words that we've seen before, can be approximated by the probability of the next word given just the preceding word. For a 3-gram model, it would be the same thing on the left, but on the right, we would say probability of the next word given the preceding 2 words. So I actually used to implement n-gram models back in the 90s, and I dusted off some code for building trigram models, and trained a trigram model on news articles, on like 60 million words of Wall Street Journal articles. And I prompted it, meaning I kind of asked it for completions for Boston weather is. And so here's what you get if you do that. Boston weather is likely to remain in a separate dispute. Shipping sources said it will cut dividend to 35,000, and so on. As you can see, any kind of 3-word window of this text is coherent. But beyond that, it starts to kind of go off the rails. So Boston weather is likely to remain is actually kind of like on the right track. But then maybe because of the training data, it starts to talk about shipping and yields and all this financial stuff. Anyways, this is just a case in point for why an n-gram model is not kind of sufficient to give us the kinds of qualities that we want in language models. Okay, so I promised to go over the last 30 years of LM research. Lucky you. The 90s kind of generally, sort of late 90s to mid 2000s, I guess, could sort of generally be characterized as feature engineering years, where maybe we had n-gram models. We went up to reasonably high order n-grams, 5, 6, 7. They still weren't powerful enough. We explored different ways of kind of clustering words and building kind of so-called class-based n-gram models to kind of get some more representational power. It did explicit things with syntax, like parsing the sentences and then using features of the parse to help in the prediction. There was a lot of work in representing the sort of topic and theme of the words that had been seen so far in a way that influenced all of the predictions going forward. And there were a few other kind of clever ways of building language models beyond n-grams as well, like maximum entropy models. In the kind of early 2000s to in the early 2000s, Joshua Bengio published a paper on fixed context neural language models. And so obviously neural nets had by then existed for a long time and had been applied sort of sporadically to language prediction tasks. But this work actually was successful at kind of beating the state of the art. And the basic way it worked is that every word was seen as being sort of represented as a feature vector, as a vector in a large, high-dimensional space. And the goal of the neural net that was trained was to learn both the weights for those feature vectors for each individual word, and also this sort of joint probability of a given output word given some fixed sequence of input words. Or another way of saying that is it would take some, fixed length context, let's say 3 words. And so like those 3 words might be whether or is vary, and then it would spit out a probability distribution over the sort of followers of whether is vary. So this did better than n-gram models of the equivalent order, because it could learn all sorts of interesting dependencies between, it could, or more efficiently learn interesting semantic dependencies between words than you could with the n-gram models. But it was still fixed context, meaning like a context of 3, like I'm showing here, it wouldn't capture if the input was Boston weather is vary. Well, by the time I got to vary, I'm already I've filled up my 3-word buffer with weather is vary, and so I've actually lost the context of Boston, and so this model might then produce hot as its sort of maximum output, which of course we know is not the case. It should be cold because it's lost its kind of awareness of Boston. So that's the kind of most kind of simplistic neural language model. But in the sort of 2010s, we revisited a concept in neural nets called recurrent neural nets and applied them to the language modeling task. RNNs had been, around since the mid-80s, but in the 2010s, we use them for these kind of sequence prediction tasks. So the defining feature of RNNs is that there's some their neural architecture with a cycle in which the output of a unit is then fed back into the input in some way, and that allows kind of an arbitrary number, an arbitrary sequence length to be the input. There's this sort of unfold operation with RNNs that I'm sort of visualizing here, but every input is kind of recognized and kind of enters into, or has something to say about about all subsequent predictions. But RNNs were also kind of too simplistic for language modeling because there's this so-called vanishing gradient problem where you would not RNNs would not be able to model stuff that had happened in the more distant past. So a big achievement in language modeling occurred in it was like 2014 or so, when LSTM, which is a architecture that was introduced in the late 90s, was applied to the language modeling problem. And LSTMs solved the problem of vanishing gradients and other problems, and I won't kind of discuss the details here. But suffice it to say, these models were state of the art up until BERT, this transformer architecture, which Shad will talk about in a few minutes. I just want to say a quick word about word embeddings because I think we'll be discussing them, or your projects kind of may end up using them in some capacity. And they were, an important contribution that, while they're not language models per se, they're often used in the same kinds of system where language models are used. A word embedding is really just a way of, word vectors are just a way of assigning numeric vectors to words such that 2 vectors are close to each other if the words are similar in meaning to each other in some sense. So the classical way of computing word vectors were just term document count matrices, where I take every document in my training corpus and I count the number of times that each word occurs, and then I do maybe some linear algebra to come up with a way of reducing the dimensionality so that each word maps to some smaller number of dimensions than the number of documents. In the early to mid 2010s, word to vec was introduced, and that was really transformative. I think I can't think of any sort of software package that's been used more by let's say social scientists for doing NLP stuff than Word2Vec, at least through to the LLM era that we're in now. But anyway, Word2Vec was a way of generating these word vectors, the same kinds of vectors that we used to generate with counts. Word2Vec was a way of generating them by using a neural net, and using sort of clever ways to kind of obfuscate the input and predict sort of the missing words, and then kind of extract after a bunch of training, extract the hidden layer depending on the application, the hidden or the output layer to use as a representation. And the Word2Vec in particular, let you do this kind of cool math on the word vectors that you could use in analogies, and you do things like man minus woman plus king equal, and then it would say queen, or did I have that right? Man minus king plus woman. Well, anyways, yeah. So you could do math on the word vectors to do some common sense analogies. So now I just want to sort of end my section and hand it over to Jad by just telling you a little bit about how far we've come. So one of the main ways of measuring the quality or the accuracy, anyways, of a language model is called perplexity. Perplexity is essentially just the the kind of entropy, or the amount of, you can sort of think of it as the number of choices, or the amount of confusion that the language model has at any given moment, sort of averaged over all of the words that it has to predict. And for perplexity, higher means worse. So the perplexity of the kinds of 3-gram models that I showed you with my little chat n-gram experiment, those, for this very famous data set called the Penn Tree Bank, the perplexity back then was in the high 100s or close to 200. We've now got it down, I mean, at least as of GPT-3, and that's actually at this point probably out of date, but it's down to like around 20 for the same data set. Perplexity can never be more than 1. If we get it down to 1, it means there's absolutely no unpredictability at all in speech. So 20 is really quite impressively good. Another way of looking at how far we've come is fluency. So here's my chat n-gram completion for Boston weather is. Boston weather is likely to remain in a separate dispute, shipping sources said. But if I give the same prompt to GPT-3, Boston weather is generally warm and humid in the summer, with temperatures typically reaching the mid-80s Fahrenheit. So this is actually a completely reasonable response, although, of course, I haven't given it any information about what day it is or what time I'm talking about. So it's not necessarily the right answer for every time. But in any case, it's fluent and accurate, at least consistent, at least accurate with respect to the time of year it's talking about. Okay, so now we've entered the LLM era, and I'm going to hand it off to Jad.